Look inside a gas turbine combustor on a test rig, and you will see a pale blue flame. Burning hydrogen produces water vapor and zero carbon dioxide, but the physics of maintaining that flame impose specific, unavoidable constraints on engineering design. For heavy, difficult to electrify sectors, like power generation and industrial heat, this fuel presents a significant decarbonization opportunity. National energy strategies across Europe, Japan, and the Gulf have explicitly named hydrogen-fired power as a primary pillar for reaching zero emissions. To make this work, engineers must move past theoretical models and gather physical data from these flames to measure how they perform under industrial conditions. This process exposes a widespread professional misconception. Because our power grids already run on natural gas turbines, it is commonly assumed that the transition requires little more than piping hydrogen into existing infrastructure. In power generation, a drop-in replacement implies you can swap one fuel for another with minimal modifications to the core machinery. Test cell data shows that hydrogen's physical properties are incompatible with the operating parameters of current turbine fleets. Engineering viability depends on whether massive hardware redesigns can be deployed at the scale, cost, and reliability required by global energy strategies. This diagram shows hydrogen's volumetric energy penalty. At the exact same pressure, its volumetric energy content is roughly 1/3 that of methane. To match the thermal energy of 1 unit of methane, you need 3 units of hydrogen. To deliver an equivalent amount of thermal power to a turbine, operators must increase the volumetric fuel flow by 300%. Handling this volume surge requires physically resizing the main fuel lines and establishing new valve authorities to manage increased flow without losing precise control. Inside the turbine cycle, compressor extraction dynamics must also be altered. The plant needs a different air mass supply to manage the new mixing ratios under constantly shifting operational loads. This cross-section of a fuel pipeline shows the limitation of partial fuel mixing. If you blend 20% hydrogen by volume into a natural gas line, you only get about 7% actual decarbonized energy output because the hydrogen is so much less energy dense. Low percentage blending offers a negligible impact on the total carbon emissions of the plant. To effectively decarbonize the grid, engineers are forced to push for much higher hydrogen concentrations, and that specific volume breaks existing power plant architecture. Moving from the fluid dynamics of the pipeline into the combustion zone itself, the next critical variable is laminar flame speed. Hydrogen's flame speed is roughly 3 meters per second at atmospheric conditions. That is 8 to 9 times faster than a methane flame. This animation shows a pre-mixed combustor. Notice the stable methane flame. Transitioning to hydrogen, the flame's high speed allows it to creep backward against the fuel flow, directly into the nozzle, a dangerous event called flashback. The hardware suffers immediate thermal damage and failure. This risk is amplified by hydrogen's wide flammability limits. It ignites at concentrations from 4 to 75% by volume in air, whereas methane has a narrow window of 5 to 15%. That wide ignition window expands the risk envelope for an uncontrolled combustion event across every stage of the fuel handling system. These physical limits clash directly with our current installed base. The large frame turbines currently generating power were engineered specifically to handle slow, predictable methane flames. Safely containing a fast, highly reactive hydrogen flame inside legacy hardware designed for methane is mechanically impossible. It dictates a total redesign of the combustor. The engineering response to flashback and extreme flame speeds requires altering the combustor's internal geometry. The current industry standard for safely burning high hydrogen fuels is known as the micromix combustor. Instead of large nozzles, a micromix design utilizes hundreds of extremely small fuel injection holes. This geometry actively controls flame liftoff and restricts upstream propagation. However, these components require exceptionally tight manufacturing tolerances. The operating windows are narrow to maintain stability without melting the surrounding metal. Retrofitting millions of residential or light commercial heating units with this level of precision is virtually impossible. The feasibility lies in upgrading heavy, large-frame industrial turbines. These combustor upgrades are expensive. To amortize that cost over decades, the plant must achieve a combined cycle efficiency of 60% or higher. Because combustion stability at high concentrations requires such precise, custom architecture, universal fuel switching across existing infrastructure is technically and economically unfeasible. Even if the hardware holds, hydrogen presents an emissions paradox. It eliminates carbon dioxide, but introduces a nitrogen oxide, or NOx, problem. This is dictated by the adiabatic flame temperature. When hydrogen burns, it reaches significantly higher temperatures than methane. The laws of chemistry dictate that hotter, faster flames inherently promote the generation of thermal NOx. For a turbine to be commercially viable, it must meet strict regulatory thresholds. The industry standard requires achieving single-digit NOx, keeping emissions below 9 parts per million. Maintaining that strict emissions threshold while running high concentrations of hydrogen requires precise combustor design and unyielding operational discipline. Trading a global carbon problem for a local air quality problem is unacceptable. Extreme thermodynamic precision is the only viable path forward for this technology to operate legally. This chart shows the primary economic constraint. While engineers have solutions for the combustion hardware, the current hurdle is the supply and cost of green electrolytic hydrogen. Unsubsidized green hydrogen costs between $2.50 and $5 per kilogram. To reach grid parity, it must hit the U.S. target of $1 per kilogram. Electrolyzer manufacturing is scaling, but there remains a disconnect between current production capacity and the fuel volumes required by large-scale power grids. As a result, the operational turbine fleet today runs almost entirely on natural gas or low-percentage industrial gas blends. Very few are running pure green hydrogen. In today's market, the term hydrogen-ready is a demonstration and readiness-building exercise. It is not an immediate climate tool. Engineers are laying the regulatory and hardware groundwork now so that switching fuels becomes mechanically viable once global supply chains mature. Hydrogen combustion makes engineering sense for heavy industry, but it is not a drop-in replacement for current infrastructure. Dictated by economics, the transition is a 2030 story. To review the technical breakdowns, combustor data, and turbine deployment roadmaps, access the materials on our platform.